Hello and welcome to this lecture. In the previous lectures, we saw first order linear ODEs and we saw how they had some nice applications. In particular, we saw the circuit applications, and we're going to move towards second order linear ODEs. Now with constant coefficients, I'll tell you what constant coefficients are. In fact, we only looked at constant coefficients even in first order linear ODEs. We'll only see that. But to motivate why second order ODEs come, let's see an example. Here is a very standard example. It's called an RLC circuit, a resistor, an inductor and a capacitor in series, and you have an voltage source and there is a switch which turns on at t equal to 0 and then currents start flowing. Okay, and I'm interested in finding out I of t as a function of t. Okay, so it's a very standard circuit problem. There are many other circuits, but anyway, this one is a very standard problem, RLC circuit. There are two cases we'll consider. One case is where Vs of t is a DC source and you have Vs of t being constant. The other is an AC source, in which case Vs of t is A times sine omega t. So this will be two cases that we'll consider, and we'll see how to solve this. Okay, so here if you use the circuit laws, you see that the voltage drop on the resistor plus the voltage drop on the inductor plus the voltage drop on the capacitor in these directions has to be equal to Vs of t. So this is true from Kirchhoff's current law, or this voltage law, or the loop law as we call it. And then each of these voltages are related to the current in some specific way. So Vr of t is R times I of t, Vl of t is L times I prime of t, right. So that's the relationship for the inductor, and for the capacitor I of t is C times Vc prime of t. Okay. So these are the three relationships. Now we can use this relationship into this equation and get one equation for I of t. Okay, how do I do that? I have to first differentiate this guy. If I differentiate this guy, I get VL prime. I have written VL prime first, VL prime plus VR prime plus VC prime equals Vs prime of t. Okay. Now VL prime, right, is going to be L times I double prime of t. So I can express VL prime in terms of I. And then VR prime is R times I prime of t. So we can express VR prime in terms of t, and Vc prime is I of t divided by C. And so all these guys on the left hand side can be expressed in terms of I. So that's why I differentiated once, because this derivative is showing up here. All these guys are showing up without the derivative. So you'll get that. So what you end up getting is a second order differential equation in I, right? So L times I double prime of t plus R times I prime of t plus 1 by C I of t equals Vs prime of t. So this is the equation that governs the current that's going to flow in the circuit once you turn the switch on. As soon as you turn the switch on, this is what will happen. So this is your second order differential equation. Why is this second order? So the I of t is the unknown function here. Vs is known. L, R and C, 1 by C are also known. I of t is unknown, and the largest derivative of I of t that appears in the equation is 2. So this is a second order differential equation. It is a linear differential equation, as in there is no powers of I of t higher than 1, powers of I prime of t higher than 1, powers of I double prime of t higher than 1. They are not being multiplied together. So they occur like that in this form. So this form is linear. And in fact, what are the coefficients? These are the coefficients. The factors that multiply I double prime, I prime and I of t are called the coefficients. The function on the right hand is called the forcing function. These are all terminologies people use. So this has constant coefficients, right? The coefficients don't vary with time. So they have constant coefficients, and the forcing function may vary with time. Depends. In the AC case it varies. In the DC case it just simply becomes 0. Okay. So this is the equation that governs the current that goes through the RLC circuit. Now there will be some initial conditions. I'll comment on that later. You need two initial conditions. You need I of some value, and then I prime also you need. You need two initial conditions for these things. You'll see why that is needed and all that. Okay. So this is a second order ODE linear with constant coefficients. So how do you solve this? If you can solve this, you can find current in circuits. Okay. So here is a generalization. What is a second order linear ODE with constant coefficient? A times f double prime plus b times f prime plus c times fx equals q of x. A, b, c are real constants. Q of x is called the forcing function, and this is how the equation looks. So this models many practical situations. I may not show you a lot of examples, but definitely RLC circuit is a fantastic example. Okay. So solutions are much more varied in structure than the first order case. If you remember, the first order case solution for at least constant coefficients and some some q of x being sine or constant for the circuit, right, for the RC circuit, the solution had a simple form, right. It was either the steady state was either a constant or it would go to a sinusoidal function, and then there will be a transient which will be usually e power minus t something, and then it will eventually die down to that. So we saw that's how the first order ODE solutions looked. Okay, so it's important to get a sense of the solution. Okay, if you have a circuit, how will the current behave? What will it be after a long time when the circuit settles down in steady state? What will it be in the transient state? Will it be too high? Will it be too small? All these things are important. If the current goes too high in the transient state, something is going to blow up in the circuit, right? So all these things are very important in engineering. So you should know how f of x is going to behave, how f of x is going to be, and how it depends on q of x, how it depends on ABC, and all of that. Okay. Interestingly, the solutions for these kind of equations involves a lot of guesswork. Based on your experience and understanding of how functions behave, you have to imagine and guess that this could be a solution, and then from there work with what's going to come out. Okay, and the guesses, specific guesses, are made based on what kind of form q of x has. Okay, so I'll show you how this can be done, at least for a couple of q of x's, and then you'll pick up the skill to do this in a much better fashion. Okay, so the first and the simplest case, once again we'll start with the easiest case and build on it do more complications later. So the easiest case is when q of x is 0. Okay, so a, b, c are real constants and q of x is 0. There's no forcing function. Okay, so this is called the homogeneous case. Okay, so there is no other function other than f involved, and there is no constant term, and there's no q of x here. So this is called the homogeneous case. So the homogeneous equation, or the homogeneous differential equation, second order linear constant coefficient, is reasonably easy to solve. And how do you solve it? You have to guess a solution and see if it works. So now, from our experience, a very good function to guess a solution for these kind of equations is exponential, right? Exponential with some sx, e power sx. We have seen that this function has a lot of good properties with respect to derivative. It doesn't do too much with the derivative, right? It gives you some very easy functions, easy properties with respect to derivative. So a very good function to guess is e power sx. We may allow s to be, we will have s to be a constant, but it can be a complex constant also. We don't mind it being a complex constant as long as there is a conjugate also coming, so we can figure out how to deal with it even if it is complex. Okay, but what value do you take for s? Okay, so that's going to depend on ABC, right? The value of s here will depend on ABC. In what way? How do you do it? You just substitute. Okay, so the guess f of x equals e power sx works if you substitute e power sx here, a times e power sx double prime plus b times e power sx prime plus c times e power sx, which is equal to, if you do some simplification, what is double prime? It's just s square times e power sx. Single prime, just one derivative, is s times e power sx. So you get this simple little equation, as square plus bs plus c multiplied by e power sx equal to 0. Now what do I know about e power sx? That is never 0, right? So we require as square plus bs plus c equals 0. So any s that satisfies this equation, you can plug in here and you will get a good guess or a good solution for this constant coefficient second order linear ODE. Okay, so that's a homogeneous case, right? So when this is equal to 0. So this is a very simple thing. From a differential equation, we went to a quadratic equation. That's the power of this exponential function. I hope you see the value of studying all these different types of functions and how they come in and solve real difficult problems by converting differential equation into a quadratic equation. I want to once again emphasize, we studied quadratic equation long ago. It was a simple thing. But notice how when you have a more complicated situation, you are just doing something to convert that complicated problem into a simple problem that you know a solution for. Okay. Once again, I hope this is a demonstration of the principle that all of mathematics is like that, right? So you take a difficult problem, a complex looking problem, you just convert it into something that you can solve. Okay, that's something we have solved before. So this is a quadratic, and you can solve it to find s. Okay, so as simple as that. So what are the different types of solutions that are possible? So the nature of the solution will depend on the type of roots that you have for the quadratic equation. You know from your experience, the quadratic equation in some cases will have distinct real roots. Okay, so if the equation, the characteristic, this equation is also called the characteristic equation sometimes based on the guess. So if your equation here, quadratic equation, has two distinct real roots, let's say s1, s2, and they are not equal, okay, distinct real. We guessed, you remember, e power sx. In this case, there are two solutions you have found for this equation, right? e power s1x and e power s2x. Okay, so these are the two solutions that you have found. So here is a very interesting and simple linear combination property that you have for homogeneous equations. If you have two solutions f1 of x and f2 of x, then a linear combination of the two solutions, this is called a linear combination. You multiply f1 of x by c1, f2 of x by c2, and then you add. Anytime you do this, it's a linear combination. So if you have two solutions, the linear combination of the two solutions is also a solution, okay, for this same equation. Okay, so you can find this out in a very, very easy way. You'll see that. So supposing if a times f1 double prime of x plus b times f1 prime of x plus c times f1 of x equal to 0, and a times f2 double prime of x. So it's a very easy thing to check that if you have both of them being solutions f1 and f2, what will happen if I do a times c1 f1 plus c1 f1 of x plus c2 f2 of x double prime plus b times c1 f1 of x plus c2 f2 of x prime plus c times c1 f1 of x plus c2 f2 of x. You see, if you do this derivative by, the derivative just goes into the summation, just the property of the derivative, and then combine things together, you see that this will just be c times a1 f double prime. I'm just going to write it in a very quick way, plus c f1 plus c2 times a, not a1, this is a f2 double prime plus b f2 prime plus c f2. Okay, and this clearly, I'm sorry, this, if you plug in here, you're getting this equal to this, which is equal to 0. So you see here, if f1 and f2 are solutions, then c1 f1 plus c2 f2 is also a solution. It's a very easy thing to check here, not too hard. Okay, so this is the linear combination property. This happened because it was homogeneous, because the right hand side was 0. If it was not 0, this won't happen. Okay, so it's an important thing to understand. So both of these are solutions. Any linear combination also is a solution. So now we have a whole class of general solutions, which are c1 e power s1x plus c2 e power s2x. Okay, so which one do you prefer? Which one do you pick, c1 and c2? This is how you do it. They come from what are called initial conditions, or something you know about the f. You typically, what you know about f will be f of x0 and f prime of x0. Okay, so you'll know these are the initial conditions. At x0, I know my solution f has a value f of x0, and I know its derivative, first derivative, has a value f prime of x0. If I know these two, I can do the substitution here. I can put f of x0 here. I will get one equation in terms of c1 and c2. I can do differentiation f prime of x, and it will be c1 times s1 times e power s1x plus c2 times s2 times e power s2x, and then I can put x equals x naught. I will get another equation in c1 and c2, and I can solve c1 and c2. So notice how it's working out very nicely. So this is very common to have f of x0 and f prime of x0. You can also have other functions. You can have f of x0 and f of x1 you may know, or f of x0 and f prime of x1 you may know, whatever. As long as you have two values that you know, you can fit a function here, exact solution that you can get finding the value of c1, c2. Okay, so known initial conditions or known conditions f of x has to satisfy, and you will get this. These are also called boundary conditions sometimes, depending on how the problem is formulated and how the equation comes about. Okay, so this is a distinct real roots case for the homogeneous equation, and there is an easy solution here. So here's an example. Just to give you a concrete example, you can see f double prime minus 6 f prime plus 8 with f0 and f prime of 0 both 1. Okay, so I want a solution which satisfies this initial condition. Initial condition are usually at 0. Okay, so that's how it works. So I'm going to solve, if I guess f of x equals e power s6, I'm going to get a quadratic here, and the quadratic will be s square minus 6x plus 8 equals 0, and clearly, 2 is a solution here, 4 is a solution here. 2 and 4 are two distinct real solutions. The general solution is c1 e power 2x plus c2 e power 4x. How do we find c1, c2? F of 0 is c1 plus c2 equals 1. F prime of 0 is 2c1 plus 4c2 equals 1. You solve it, you get c2, c1, and you plug it back in, you get f of x as 3 by 2 e power 2x minus 1 by 2 e power 4x. You can substitute, once you get a solution, you should plug it back into this equation and check that it actually checks out, and you get all these conditions that you want. Okay, so you see a very simple example. The next possible case for this quadratic is to have repeated real roots. Okay, so the quadratic equation you have may be a perfect square, right? It may be some, some s plus b whole square or something like that, right? S plus b by 2a whole square. It may be that. Okay, if it is a perfect square, then you will get two equations, two row roots repeating. Multiplicity will be 2, right? You will get s1 comma s1. Okay, so this is a real, both are real, let's say. So then you have only one solution, e power s1x. How do I tackle this case? Okay, so here is a very interesting property. If you have real repeated roots, if you have e power s1x as a solution, x times e power s1x is also a solution. Okay, so this you can check quite easily. You will see that this will come out very nicely. I can show it to you, but then anyway, I mean you'll see how it works out. If you just substitute x times e power s1x, work out through this, and you'll see this will also be a solution as long as s1 is a repeated root of this quadratic equation. So the reason is, if s1 is a repeated root of this, if you take a derivative of this guy, s1 will be a root of that also, right? That's the important property here. If you take a derivative here, what is the derivative? 2as plus b equals 0. So s1 will also be a root of that. 2as1 plus b will also be equal to 0. Okay, so you keep both of those in mind, and then you plug this back in here. You will see x times e power s1x is also a solution. This is an exercise. I'll urge you to try it. So I have these two looking solutions, these two nice looking solutions for this homogeneous equation when you have repeated roots. So what do you do for the general equation? When you have two solutions, C1 times one solution plus C2 times another solution is always a solution for this homogeneous. I'm going to use the same principles over and over again, so I get an equation. So I get a general form for the equation with C1 and C2. So now I can plug in my initial conditions and find the value of C1 and C2, and I'm happy about it. Okay, so here is an illustration of this, f double prime minus 6 plus 9 this time. And this 9 again has the same initial conditions. So now we have to solve s square minus 6s plus 9 equals 0, and in this case the two roots are repeated, 3 comma 3. So I know my general solution is c1 e power 3x plus c2 x e power 3x, and f of 0 has to be 1. That gives you c1 equals 1, right? X is 0, right? And then you have to do a derivative. Derivative takes a little bit of effort. I mean, just make sure they use the product rule here. Here it's okay. You will get 3c1 plus c2 equals 1. And then you can solve from these two to get c1 equals 1, c2 equals minus 2. And the solution here you can combine, right? So e power 3x is common in both sides. So the solution is 1 minus 2x times e power 3x for this differential equation. Okay, that's two cases. The final case is complex conjugate roots. This is a very interesting case. So you have a homogeneous solution like the equation like this, and you go ahead, guess the e power sx, and you find the quadratic, and you have two complex conjugate roots. Okay, so you know that that's true, right? A, B, C are real constants. So if you have two complex equations, they have to be complex conjugate pairs, right? One has to be the conjugate of the other. If you have one complex root, its conjugate will also be a root. You just take conjugate here, you will get that. Okay, so this is a property. So you can actually continue now. I mean, it doesn't matter. I mean, e power complex number also we are okay, right? We know how to do that. We have complex arithmetic in our hands. Once again, I want you to see how all the things you learned are coming together, right? Polynomials, complex numbers, functions like exponential, all those things are coming together, derivatives in this final application to show you how to solve a real practical problem like solving differential equation. So the solutions are e power r plus it, which is e power rx times e power r plus it into x, which is e power rx times e power it into x. Okay, so this I know from my complex exponential that this is e power rx cos tx plus I e power rx sin tx. The other solution is e power rx e power minus itx, that is this guy, right? E power r minus it into x, which is e power rx times e power minus itx. This will become e power rx cos tx minus I e power rx sin tx. So notice that these two solutions are themselves actually linear combinations of two other functions, e power rx cos tx and e power rx sin tx, except that the combinations now are allowed to be complex numbers. Why not? We are happy with complex numbers. We know how to deal with complex numbers. So we'll allow that. So these equations themselves are linear combination. So much better set of solutions for this case, in the complex case, which comes out to be real and nice, is these two solutions. By the linear combination property, you can see that for this equation, if you have complex conjugate roots, actually e power Rx cos Tx and e power Rx sin Tx are solutions. You can just take linear combination, you add these two, you will get e power Rx cos Tx. You subtract these two and divide by 2i, you get e power Rx sin Tx. By the linear combination property, both of those should also be solutions here. So once you have that, you have this remarkable simple looking functions e power Rx times cos Tx, e power Rx sin Tx. Okay, so we'll do some plots a little bit later to see how these functions will look. Okay, so these are very interesting functions. These are important in circuits because these functions show up in circuits a lot. You'll see them. Okay, so this is a important and interesting case that you have here, and this comes as the solution for the complex conjugate roots are there for this equation. Okay, so the general solution is C1 times this solution plus C2 times this solution, but interestingly I can take the e power Rx common outside, so I get e power Rx into C1 cos Tx plus C2 sin Tx. Okay, so once again C1, C2 you find to satisfy the initial conditions. Okay, so let's go back to our example here, f double prime minus 5 f prime of x plus 8 f of x equal to 0, f of 0 equals f prime of 0 equals 1. This is my initial condition. So if you do roots here, you see that this becomes complex conjugate. Okay, so you can see 25 minus 32 is negative, so you will get this. So S is 5 plus or minus root 7i by 2, or 5 by 2 plus or minus root 7 by 2i. So what are my solutions? What is my general solution? I know it's e power 5x by 2, right, e power Rx times C1 cos root 7 by 2x plus C2 sin root 7 by 2x, right. So root 7x by 2, root 7x by 2. This is my general solution. How do I find C1 and C2? F of 0, you know what, how to evaluate f of 0 and all that. These functions are known to you. Sin 0 is 0, cos 0 is 1. This is 1, so C1 is 1. F prime, again you have to differentiate. Now you have to use the product rule with e power and cos, right? And then go ahead, substitute. I've done all that for you and finally given you a simple formula. But make sure you check this. Okay, make sure you check all these derivatives, and you got f prime of 0 to be 1, this function to be 1 here. So you go ahead and solve, you will get C1 is 1, C2 is minus 3 by root 7, you plug it back in, you get the solution is e power 5x by 2 times cos root 7x by 2 minus 3 by root 7 sin root 7x by 2. Okay, so this gives you a glimpse of how the equation comes. So notice how the second order ODE has a different structure in the equations. It has very nice simple at the end, but you have to do some guesswork. And the homogeneous case, if you guess e power sx, you get a quadratic equation, and you solve the quadratic equation depending on the 3 different roots, that is depending on where the quadratic equation is, quadratic function is, you will be getting 3 different types of solutions, right. In one case you have just sum of 2 exponentials, in the other case you have exponential plus x times an exponential, the other case you have e power exponential times a trigonometric function, sinusoidal function, e power x into cos or e power x into sin. So these are important things to remember in your mind. Okay, for a second order ODE homogeneous case, these type of solutions will come about. Okay, that concludes this lecture. Thank you very much.